Hello and welcome to the Terminology Leading Practices stream of the SNOMED CT Expo 2020. My name is Kathy Richardson and I'm a Senior Terminologist at SNOMED International. I will be moderating today's session. Please use the Q&A box located on the left of your screen to type your questions to the presenter. Questions will be answered at the conclusion of the presentation. I'm now pleased to introduce Dion McMurtrie from CSIRO, who will be presenting Invariants, how to test SNOMED CT content development. I'll now pass over to Dion.
Hi, thanks Kathy. So my name is Dion McMurtrie. As Kathy mentioned, I'm presenting this on behalf of the three of us, so Michael Lawley and Matthew Cordell, my colleagues from CSIRO and the Australian Digital Health Agency, who we all worked on this topic together. It's just practically easier for me to do all the presentation. So I'll just go quickly through the agenda of what I'm going to cover in this presentation. We firstly go through an exploration of the content modelling approaches and various modelling approaches and their trade-offs, particularly looking at the way that they deal with existing content problems or detect those, and how refactoring and maintenance works. Then I'll go through and introduce and examine the idea of this invariance as content tests and how they can balance some of those trade-offs. And then I'll go through a few examples of the approach of demonstrating those modelling approaches and the invariance. So modelling approaches. This is a screenshot taken from the SNOMED International Confluence page on authoring, which talks about the modelling philosophy in SNOMED CT, which is probably familiar to most. It's a zero-based proximal primitive approach to modelling, where the author will state a proximal primitive supertype and then go and model a reasonably large amount of modelling on top of that, because the proximal primitive supertypes are often quite high up the hierarchy. And then the classifier will go and infer the appropriate more proximal supertypes. So I guess the first thing to note about this is proximal to what? And I suppose this belies the fact that there's really a step zero, which is the author planning through what they intend to do and probably identifying where they intend this to end up in the hierarchy anyway. So I guess the point from that is that authoring is more than the process of just stating the stated form. There's a certain amount of thought that goes into and planning that goes into authoring a new concept or concepts. So the real question here is, how do we capture some of the outputs of that process that currently aren't captured in stated form, and how can we use those to our advantage? So first, looking at proximal primitive modelling, which is the way that the SNOMED International models the international edition. This again is taken off the wiki page for the proximal primitive modelling from SNOMED International, and is as I described, using the most proximal primitive supertype or supertypes, and then adding additional refinements on top of that to fully define the concept. In the example, these are taken off the wiki page. There's computed tomography of humerus, which is based off the procedure concept, which is quite high up the hierarchy, and then refined down using a procedure site and a method to ultimately infer the additional parents. So looking at benefits and disadvantages, and really the number of these things really isn't meant to indicate anything. Some of these are smaller and larger than each other, and there's actually double sides to a lot of these. But the benefits really are that you get this uniform stated form, which is much more amenable to a programmatic transformation. And you also have the ability to use modelling via templates and have quite a structured modelling approach to have that uniformity. I guess the disadvantages are it's much easier to miss proximal primitives or particularly new intermediate primitives that get inserted over time. It's easier to miss statements that might infer other defined supertypes that that probably should be there, that might not be. And we're getting humans to state a fairly mechanical form rather than a more human form. And this form is actually the proximal primitive form is quite mechanically derivable. There is quite a lot of redundant restatement, and that's a feature of choosing a very high concept up the hierarchy to then refine. You're not picking up the additional refinements that are in parents that will be inferred after the classification. And that can make refactoring harder. However, that's double-sided because it can make the really structured stated form actually makes it quite a lot easier to programmatically transform the content. So that's a very double-sided issue. Ultimately as well, templates are very necessary to scale this approach, and they also require maintenance, and there's quite a lot of them. And we need to transfer any existing content to make it conform to those templates. Looking at the authoring page on the wiki, it actually calls out the advantages of this approach being enhancing the ability to maintain content, and I think that really relates to the benefit that I stated there about being able to transform that content programmatically, which is certainly very true. The statement about supporting identification of equivalences it seems a little odd because effectively that's what a classifier does. I suppose this is referring to being able to detect that within the actual stated form itself prior to classification. However, in the face of additional axioms like GCIs, it becomes, I guess, a little bit more difficult. So having a look at another approach, and this is a name that Michael and Matt and I have come up with to compose and refine, but effectively to compose the meaning out of existing concepts that are much lower down in the hierarchy, sort of at sensible minimal proximal parents, and then to state on only the required additional modelling on top of the meaning that's taken from those concepts. So again, this is using the same example that came from the wiki page from SNOMED International. Instead of the procedure parent, we're taking on the CT of bone as a parent. Unfortunately, because of the role grouping, it's necessary to not just state the procedure site as being the humerus, but we also have to state into the role group the CT again as the method. But we ultimately end up with the same result. And I guess another observation here is that while templating isn't really at play here, you could also use the idea of having a certain list of concepts that are good candidates to template off rather than having an actual template library and associated maintenance that comes with that. So looking at this approach, some of the benefits of this are that there's less redundancy, it's more concise, there's easier refactoring from inheriting things from the ancestors rather than needing to have a lot of restatement. So there's less need for that programmatic refactoring. And it's much less likely to miss inserted intermediate primitives because they'll be picked up through the parents that are stated much lower down. Disadvantages, it's much less uniform, therefore it's much harder to do mass programmatic refactoring, but maybe less necessary as well. So again, that's a bit double-sided. It may mask some modelling issues in the hierarchy above, which I'll go into a little bit more detail in a moment. And it certainly does rely on humans to pick good minimal parents, which I suppose so does proximal primitives, although that's a lot easier to do because there's fewer candidates. And there's that risk of the role grouping not working. As I mentioned, you needed to restate that role group for the CT of humerus, although that becomes apparent in the classification, and the example I have further on covers that. So in this case, templating, the templates are interesting in that they become almost patterns of conformance, right, more than something that you might use as a prescriptive stated form. And then there's a more extreme example, which I won't spend a lot of time on, but maximal modelling. So effectively modelling out everything, all of the parents you can think of that make sense, plus all of the additional refinements that need to be made to model out the concept fully. The benefits of this are you're very likely to pick up all of the modelling and all of the ancestors that you need, and you'll probably reveal unintended consequences as part of doing that, which is good for picking up errors. That said, you might actually mask some of those in the same way as the previous approach, which I'll talk about more in a moment. And there's a lot of redundant restatement, which makes it very difficult to manage that content and mitigate with automation. Although I suppose you could mechanically reduce to the proximal primitive modelling if you needed to. So I guess the real question is how do you get the advantages of all of these approaches without also taking the disadvantages of them? Is there a way to do that? So before I go into invariants, I'll just talk more about what I mean by masking the parent modelling issues. And this is a super simplified example. So if we're looking at the modelling of this lower down concept that we intend to end up with a square, a triangle and a circle, and we're saying that it's inheriting down from these ancestors. Ultimately, if we state the square, the triangle and circle, that's what we'll get in the result, and that will be correct. However, we're not picking up that this parent that has just the square should actually be giving us the triangle as well. And that's really what this is trying to indicate. Because we've stated so much, we're not going to pick up the fact that we're not inheriting something we think we probably should be. So if we take a more minimal approach where we say we just state those two parents and expect to inherit those down, we miss the triangle down in the child, and so they're both wrong, which gives us the opportunity, if we've got that expectation, to be able to spot that. But we need something to be able to detect that missing expectation. And if we state it in the stated form, we will just get it in the inferred form. So that's not really the way we want to do it. We want to let the inferred form not have it if it's not going to get it, but detect that has happened. And then we know that we've got two problems. So once that's detected, we can then go back and fix the parent. And then ultimately we end up with both the ancestor and the child having the modelling that we intended. So having a look at an example of the invariants. So the idea is that they're unit tests for concepts, essentially. So regardless of the modelling approach that terminologists use, they do come into the process with expectations that are formed during the modelling. After classification, terminologists will review those inferences, and they'll often form opinions then about whether those inferences are correct or not correct or incorrect. And they form another thing that you can check later on. So stating all of these things, which you can only make positive statements, you can't make negative statements that this thing that's been inferred isn't true and should never be true. But it can, if you try and state all that, you can end up masking all of those additional problems. So each modelling approach can actually benefit from these, and that those unstated statements that are expected or known to be true, they can be used as content tests for any of those approaches. So an initial set could be stated even before the modelling was performed, and the classification can then hide any of those broken assumptions, a bit the way that we would with software. So continuing on into an example, acute appendicitis. So this is the way that acute appendicitis is stated in the International Edition against the proximal primitive parent disease with the associated morphology of acute inflammation and then a finding site of appendix structure. So that infers, much as we'd expect, that acute appendicitis is an appendicitis. But if we have a look at some of the other concepts that are similar, so looking at acute infective endocarditis, we'll notice that it's a descendant of both acute disease and acute inflammatory disease, which really acute appendicitis should be too. So where have these gone? So looking at acute infective endocarditis, you actually see that it's got a clinical course modelled against it, as well as the other modelling and the parent of disease. And if we look at acute inflammation and acute disease, you'll see again that there's a clinical course model there that is missing from acute appendicitis. So if we take the kind of compose refine modelling approach that I mentioned earlier, and we can take a sort of a naive first position here of saying that acute appendicitis is an appendicitis and it's also an acute inflammatory disease, and see what happens. So obviously, when we classify that, we'll find that we've got a problem here, which is that the role grouping hasn't worked out between the associated morphology of inflammation and the acute inflammatory morphology. So that's a trigger for us to go and try and fix that, which I'll show on the next slide. Interestingly, also, we picked up an unexpected parent here of acute digestive system disorder. So when we refine that further, ultimately we get the expected classification. Although we've picked up this new acute digestive system disorder, which is probably not something that we'd state as an invariant, as something that should always be that way, but it's come through in the classification results. And then ultimately, the idea is that we've picked up this clinical course through stating that parent and inheriting that, and other sorts of refactoring can flow in that sort of way. So looking at a possible implementation for invariants. So invariants are really just statements about a concept or concepts. We can use ECL to do that, and we can effectively expect that ECL to subsume or not subsume that concept. So that can be used to create a negative statement. Invariant statements can be checked after the classification result, and the statement should be used to check the distribution of, for example, the international edition, but it's something that should just be passed down to extension builders off any edition so that they can then also check any changes they're making to test their extensions. Statements would look very, very similar to modelling, but not necessarily be part of the stated form itself, which means that it won't interfere with the classification results. So it's intended to capture the author's intent as an explicit positive or negative statement, but doesn't require them to overstate the concept definition, which will interfere with the classification results. So using the invariant example for the example we just went through, acute appendicitis, so we can make these two statements that acute appendicitis should always be a subtype of appendicitis, and it should always be a subtype of acute disease. And what I've used here is a FIRE request using validate code operations to validate that the ECL-based implicit value set contains the code of the concept that we're interested in. And this can be added to the proximal primitive modeling, and it will detect that particular issue. So looking at what happens when you run those queries, this is the result of the first one running against OntoServer, which shows that indeed acute appendicitis is a subtype of appendicitis. And this is the second one, which is showing that it isn't an acute disease or acute inflammatory disease, which is not what we wanted. Taking a further example, we can look at acute and subacute endocarditis, and we can see here that it's an acute, both an acute endocarditis and a subacute endocarditis, and it's got the clinical courses that we would expect. But having a look at both the subacute endocarditis and acute endocarditis concepts, the subacute endocarditis actually is a descendant of subacute disease, but acute endocarditis isn't an acute disease. So why has this happened? And it's much the same thing. The stated form of subacute endocarditis includes the clinical course, but acute endocarditis does not. So again, we can use similar examples of ECL-based invariants to say that acute endocarditis should always be an endocarditis, and it should be an acute disease. And I won't bother showing the examples of those, but it's much the same pattern. The ECL in these examples are very, very simple, but it could be as complicated as you need it to be to say whatever it is that you wish to say. Taking this one step further, we just had a bit of a look into the acute morphology. So you can see here that there's 94 acute morphologies. I'm just looking for that ECL, looking for morphologies that include the term acute, executed against ontocellular. And you can see if we look at concepts with acute in them that have a morphology that is acute, but aren't acute or subacute diseases, you can see there's 152 of those. And then if we take that further and say remove the constraint that the concept needs to have acute in its name, you can see there's actually 251 of those. So that these probably need looking into and may already be known. So looking into the benefits and recapping, effectively the benefits of stating these invariants is that it doesn't mask any modelling issues through overstating and trying to pack these particular statements you want to be true into the stated form. It means that the inferred form can have the flexibility to actually not find these particular things that you want, and you can check and find defects that might exist somewhere else. It allows for those different modelling approaches. It works with any of those modelling approaches that we talked about. It's just that the things you might be stating might be different or might actually be quite similar. It provides, importantly, a backstop for refactoring or future modelling. It does that by highlighting the important changes in inferences and separates them from sort of stylistic or distribution changes that might happen over time. It helps spot particularly new intermediate primitives that are particularly relevant in the proximal primitive modelling case. And you can make negative statements as well as positive statements, which are a little bit more difficult to do, particularly in the stated form. And I guess the concept overall is just akin to writing unit tests that sit alongside code. And again, in that in code, you wouldn't be trying to effectively write a unit test for every single thing that's inferred in the inferred form, because that's too brittle and too rigid. You're really looking at identifying the key things that you need to make sure are always true and allow the rest of the inferred form to be able to flex with its distribution form underneath that. So that's the end of the presentation. Thanks very much, and I'll hand back over to Kathy.
Thank you, Dion, for your interesting presentation. Can I ask that attendees give us a moment while we switch over from our pre-recorded content so that the presenter, Dion, and Michael and Matt can address the questions you've been submitting live. Please also note that this session will be available on the event platform for the next 3 months. Thank you.
Hi, and thank you for that presentation, Dion, Matt, and Michael. Now, we've got a couple of questions here ready to ask you, and if anybody else out there has any other questions, please pop them in the chat. We've got about 6 minutes for questions. Okay, starting with the first one that came through. How much of a role do you think tooling plays in effective modelling? How could we improve the quality of tooling to improve the quality of the terminology?
Look, I guess you're asking exactly the right or the wrong person for that question. Tooling is very dear to my heart, I suppose, and probably Michael as well, and even Matt, even though he's on the dark side. I think, yeah, it plays a massive role, and in lots of different ways, to make it clear to the modelers what's actually happening, to make it efficient for them, so that they can see the important things from the unimportant things. I suppose in this case, one of the things that plays into this, and given we've worked on tooling in the past, is when you see your classification results, how those are represented, often in terms of how the distribution normal form might be affected by what you've chosen to do, and it's that can create a lot of white noise depending upon how that's rendered. to someone. So it might be really, really difficult to pick from out of those things which are the important things, and they might get fatigued looking through all of those things and miss important things. So I guess that's partly why this is effectively a tooling suggestion, to say that this is something that we can sort of steal from the software industry and say that if you can write these tests, these expectations about how you expect things that should always be true or are really important to be true, while still allowing some flexibility to move, then it makes it easier to spot the things that are important that go wrong. I don't know if the other guys wanted to comment on that.
Yeah, I think you're right. We obviously feel that tooling is essential, but moreover, it's process and tooling supporting process, and I think that's really what we're sort of arguing here, is that the approach you take really has an impact in the results you get. And personally, and again, this reflects my background, I think that software engineering has a big set of experience to draw on for modelling, and we should look at what's done in the software engineering space to produce quality software and apply that in the modelling space.
Okay, well, we'll move you on to the next question. Got a great presentation there. This approach is similar to the unit test. What is the size of invariance reset? How do you identify invariants for coverage? And how do you know the invariants covered the closest parents? Now, there's 4 in 1 there, so you can see that.
Sure.
Bigger question.
Yeah, well, look, I think the point is, and that's why it's interesting to look at those different modelling styles and how they can effectively make errors in different ways and can mask different things. And I guess without getting into which one's better, they've all got, you know, a weak spot or a blind spot. You know, I think if you're taking that example, you can make assertions. You know, you might not want to make an assertion that acute appendicitis is an acute inflammatory disease if you know, maybe that's some intermediate concept that may not always exist. I mean, I'm just picking out as an example, but it's pretty clear that it's always going to be an acute disease. And so adding that, if you've modelled it one way, and adding the natural conclusion as something that shouldn't shift around, even though that is probably going to be an ancestor that won't come out in the distribution normal form. You want to make sure that whatever parents it does inherit do end up in that ultimate parent. And so, you know, there's a tension there between making your test too specific and therefore brittle versus making sure that you're covering everything you need from that concept. And I think the other really important thing about them is being able to hand those down to extension builders as well, so they can validate that the changes that they've made haven't actually broken anything important. I know that they can look at what changes have happened in the distribution normal form, but again, teasing that apart to find out exactly what the key bits of that were versus from the white noise can be trickier than it might seem.
Okay, we are coming up to needing to end the presentation, so I'm going to have to say thank you very much, guys, so we can move on to the next section. But thank you, it was a good presentation.
No worries, thanks.
Thanks.
Thanks.